Right. Okay. These are two methods that are used quite a lot at like the high level of scientific computing, the kind of thing you're going to be doing. So far we've been talking about the general question of, if I've got a set of steps I want my computer to do, how do I make that happen faster? But what we really care about is science results, not particularly about like, is it doing these specific steps? So our driving question is going to be, can we change the like individual steps that we're doing in order to get the same or better science results? So to be a little more specific, we're going to be talking about how efficient a function is. So anyone have an idea of what that could mean? And I've got like the generally established like answer to that question roughly down here, but before that, let's talk about what it could be.
Perhaps that it takes less time to do the same thing.
Okay, yeah. So takes less time than what?
Than it previously did, I guess.
Yeah, yeah, than a less efficient function or whatever. Less time. Different function. That's a good one. I really like that. Okay. But the amount of time that it takes for a program to run is going to be really dependent on the computer you're running it on, right? Because if I run something on like the supercomputer up at LBL, that might take like a bunch, like milliseconds, whereas it would take like hours on my laptop. So that's not really like a universal measurement. So any idea how we can make that a universal measurement? Well, this one's kind of hard to get to just by guessing, so I'll say it. One way of doing it is to count up like how many steps would you do if you were doing this by hand. So, which is to say, if I like wrote out the state of a program or whatever at every step, how many steps would I need to do? So that's a little abstract. So let's look at what the classic example of this is, or one of the many classic examples. This is a very standard topic in like data structures and algorithms classes, and it's sort of the foundation for a lot of computer science-based analysis. So, and there, one thing they talk about a lot is this example of sorting a list. So, so really easy participation here. I want to sort this in ascending order. What do I put in?
Wait, like 10, 26,
Yeah.
31, 44, 58.
10, 26, 31, 44, and 58. Yeah. Okay. Now, slightly harder question. How did you do that?
I just I checked from left to right. I found the smallest number. I put it there. Then I did the same for the next number.
Yeah. So good on you for being able to like exactly identify how you did it. Like, oh, sorry. Christian also put a definition in the chat of a ratio of how fast it runs in a single thing versus how long it takes to scale it. Yeah, you're getting to the asymptotic part. You guys are already ahead of me today. Okay. Yeah. Okay. That's a really good definition too. I like that. Okay. So you were a bit more precise than maybe I would have been able to in how you did that. And it turns out what you just described is an algorithm that's called selection sort. And so here is that in pseudocode of like, I'm going to go through 1 to n. I'm going to go through like each of these items in turn. For each one of them, I'm going to find the minimum of like the rest of the list that's not yet sorted. And I'm going to call that j, and I'll swap I and j. So this is how it'll look to the computer. So let's run that together. I'm going to go through this. I'll find what's the minimum value over here.
10.
It's 10. So what do I do?
Put it in the first position.
Okay. And what happens to the thing in the first position?
It goes to the other position where the 10 was.
It goes to where the 10 was. Yeah, exactly right. 26, 50, 58, 31. Also, I'm using one indexing like Julia because we're going to be using Julia code to actually visualize this in a bit. Okay. Next up, I'll leave the pseudocode over here. What happens next? You can just tell me this thing swaps with this thing.
26 swaps to 44?
Yep, because 26 is the next smallest one. 44, 58, 31. Okay, what next?
Then
So Azar,
go ahead.
31 swaps with what?
44?
Yep. Again, 44 is just moving further and further down. So I'm just drawing out here in red the part of the list we're going to look at. 10, 26, 31, 58, 44. And then you're just looking at the last two and seeing they're out of order. So I'm just going to put them in the right place. 10, 26, 31, 44, 58. And we're done. Okay. And so here's what that looks like in like Julia code form. So we're going to be working with this in a minute. Take a minute to like look at it, and we're still getting used to Julia syntax. So see if you spot anything like maybe that you didn't expect, or that seems strange or not like Python, anything that seems like interesting. I think there's one feature of interest here that's a little bit different than how I just described it to you. Any thoughts? Okay, well, the thing I was going to point out is over here, I have this little thing for finding the index of the minimum when I could just run like min or argmin. I could do like index of min of the array. But I'm going to choose not to do that because I want as few like external things as possible. Like length is a pretty standard operation over here and here. But other than that, I'm just like moving bits of, I'm moving objects in memory around. So I want as few like black boxes as possible when I'm doing this analysis that we're about to do. Okay, next question. Do we think this is like an efficient method? And maybe if you've like looked into sorting before, you'll know the answer, but like what do you think? How efficient does it feel?
I don't think so. I mean, because at most it'll take n-1 like times to do it, and that seems kind of long, especially if you have like a really long list.
You're again getting ahead to the part where we're going to actually put numbers to this. Yeah, I like that. It doesn't feel very efficient, but not because of the like outside loop. We'll see in a bit that like all sorting has to have at least like one loop over everything in some way or another. And what that means exactly, I'll clarify. But yeah, we have the sense that it doesn't exactly feel very fast, just because you're looking at like, well, my intuition would be like we're looking at like a lot more than I like need to. Like I'm going through like the whole of this thing and picking out the minimum. I'm going through the whole of this thing and picking out the minimum, the whole of this thing. And that's not much to do when there's like 5 steps. But what do I do when there's 5,000 or 5 million? So we have a sense that maybe we could do it a little better. And I want to put like math to that. Not very. Yeah. So over here, if I had to do this over 1 million things, we should look back at like what the actual code is doing here. I'm going over I is 1 to the end. Oh. Yeah. Yeah, I'm going through I is 1 to the end. I'm saying the minimum index is the one I'm starting on and looking to that element's right. And so I have to check, like on the first iteration, I have to check 1 million things. And on the second iteration, I have to check 999,999 things. The third one, I have to check like that minus 1 more. So you feel like you're repeating a lot of work. If we're just like scanning through this list, like if we're just scanning through this initially, we probably see, okay, 58, we probably like pick up some features just because our brains work that way. We pick up 10's the smallest one. There's like some amount of spread between them. The biggest one's 58, probably pick up 44 is also pretty big. So you get like sort of a heuristic idea of the relative sizes of things. Whereas the way it's done right now is sort of dumb in a way, because it doesn't like remember anything. It doesn't remember that there's a 26 here, for example, and that it can use that next turn. So maybe we have a sense that it's not like very fast. So our answer here is just slow with the letters spaced out for emphasis. Okay, I want to put math to this idea, and Christian's already alluded to how we might be able to do that by talking about in terms of n, how many it'd have to do. So let's try and do that. So over here, let's try and like compute the cost in terms of like numbers of operations of this function over again. So I'll say that like if I'm putting something into memory or taking it out of memory or swapping or something like that, that takes like 1 unit of computation. And if I'm looping, I'm doing 1 unit of computation many times. So let's start over here, like really easy. This if, how many units of computation is that?
2.
Yeah, something like 2, 1, and 1. We'll see that the exact numbers don't really matter. So you could argue like indexing into the array is 1 and then comparison is 1. So this is really 3, but like it doesn't take like noticeably longer to just get this array element versus to do this computation. So we'll call it 1. Okay, so I've got a loop in here that's taking 1 plus maybe 1 more. 0, 1, call it that. How about this inner loop, the one over j? How much does that take? It's just how many numbers does it go over? Because we've seen that like within that, it's going to be 1 or 2 each time. So it's ending at like length of the array and it's starting at I plus 1. So I'm going to say length of the array is n. So this would be like n minus I plus 1 multiplied by this thing, the 1 plus or maybe 2. Over here, I'm going to call this 2 units because I'm doing a swap. And I'm going to call this 1 unit more. And then over the whole thing, it's like n. So now I've got this like weird combination of things that are taking up variable amounts of time. I have to do a summation over these n minus I plus 1 times either 1 or 2, or either 3 or 4, however you want to count it. And there's a lot of like subtleties and ambiguities to this, and it's sort of obscuring the main point. So you could come up with a sum. I guess in this case, it'd be something like n squared over 2 plus 3n plus 4. I'm completely just making this up, just very roughly. It would look something like that. It would need that many operations. But we don't really care about that. We don't care about these extra factors of the constants, partially because it's a pain to count them up, partially because it doesn't really matter for performance. Like, if I'm running this on something where it's small enough that this matters, that these terms matter, I don't really care that it's going to take that little extra bit of time because it's going to be basically instant anyway. What I care about is what happens when I go out to like 1 million or 1 billion. And so what we do in asymptotics is we just take the order of magnitude of this process. And this should be like very familiar to us from like math and physics. Like physicists take order of magnitude approximations all the time. So this is really like in the spirit of scientific computing here. So the idea here is I'm going to take an order of magnitude estimate. Oh, and I just left this whole page blank. Very nice. If I have something like n squared over 2 plus 3n plus 4. And so I'm going to say that that's in. Okay, first of all, are we okay with the idea that this takes about n squared amount of time? Meaning like if I double the problem size, it's going to take 4 times the amount of time. Because there is a little more math I can put to that. Okay. I think I'll just do it anyway, though. So let's say I have, so I'm just ignoring constant factors right now. And I have like n things. I'm looping over I as 1 to n. And I'm doing n minus I plus 1 units of computation. So the total number of units of computation is the summation. That look familiar to anyone? Well, maybe if I split it up a little bit, I'll get, I don't know what that equals. I can do n squared, and I'm pulling out all the ones, and do minus n minus this thing that looks like I is 1 to n I. And is that summation, have we heard about that from anywhere? Do you remember a story about Gauss being forced to add the numbers from 1 to 101? Okay, Christian's saying yes. Pablo's saying yes. What is it? Or like order of magnitude, what is it? Okay, so if you remember the thing was, you can visualize it something like this. I have 1 plus 2 plus 3 plus 4 and so on like that. Yeah, the n over 2 thing, what you're thinking of is like how many squares are in this, and you see that this is basically like a triangle, so you can use the triangle area plus some correction for like the half ones. And you get n plus 1 over 2. And so in order of magnitude, that's just like n squared over 2. So I'm doing n squared minus n squared over 2. So I can say that's approximately n squared over 2, which in m is n squared. So I'm dropping constant factors just because like if something's taking like of 1,000,000 times the computation time, I don't really care if it's taking 2 million. It's taking like way too long, or like you're not going to notice a difference in execution time between like a millisecond and 2 milliseconds. So we're just going to say constant factors of any kind don't matter. And there's a little more math to this, but essentially you can just say in order of magnitude it's this. The notation that people use for this is there's 3 of them. So there's this for a lower bound, the capital omega. There is this for an upper bound, the big O, which you might have seen also in like Taylor expansions where you say like f of x plus delta x is f of x plus f prime of x delta x plus order x squared. It's kind of the same idea here. And then this one, capital theta, is both of them together. So in this case, we're going to say selection sort is in O of n squared. I'll write that as a full sentence just for the first time we're seeing it. Okay. So, okay. Pablo asked a good question in the chat. What if you have a process where all the steps have n to the 4th plus n cubed plus n squared steps? Yeah, and you keep it as n to the 4th, because you're right that n cubed and n squared are bigger if they like are able to dominate, but just plug in a number for reference and see what happens. Do like n of 10,000, like plug in 10,000 to that expression, and it's like basically the same as just n to the 10,000 to the 4th, plus some things that just don't matter at that size. It's like saying, if I've got a computation task that's going to take 12 hours, I don't really care if it's 12 hours and 1 minute, even if a 1 minute computation task in itself might be a big thing. So we are fine just taking the biggest factor. Okay, selection sort is in O of n squared. Why am I not saying it's in theta of n squared? Also in like informal usage, which a lot of computational physicists are very informal about this. In informal usage, you just say O to refer to all 3 of these, but O should only refer to like an upper bound. Okay. Is it in omega of n squared? Can we think of like a case where this isn't necessarily true, where it doesn't take all this work.
Is it the one where it's already solved?
Yep, where it's already solved. Then, and I think I could have written the actual implementation a little more efficiently for that. A lot of sorting algorithms out there, I think, check to see if it's already solved, because that's a O of n problem. So we say it's in omega of n, because that's the minimum amount of time it will take. And we use theta to refer to when the lower bound equals the upper bound, when I'm in omega of something and O of something, and those two things are the same. Yeah. Okay, so now that we have this basic framework, let's apply it to something a little more sciencey. This is the fast Fourier transform. So this will need a little bit of like linear algebra type thinking, just in the sense of, well, not even really. It'll just need the idea of like holding things in a vector, which we've been using since like homework 1. So, and I checked the survey. I think we've all done at least something like Math 54. So it should be good to do this. Okay. So an operation we care about in science a lot is the Fourier transform. It's used in all kinds of things, in like processing radio astronomy data and weird kinds of data analysis. And I've used it for like fitting vibrations when trying to control the telescope. There's all kinds of crazy applications here. And we don't have to care like why it's used though. All we care about for now is that this is an operation that some people like to use a lot. So it's defined like this, and hopefully my capital X's and little x's are distinguishable here. This one's capital, this one's little. I'll try to do little x with the script. So if I've got x, little x, an n-length array, then its Fourier transform, like this sort of script f of x, is also an n-length array, where you have like this formula for every one of the constituent elements in the transform. Okay. Suppose you want to compute this just by like actually doing the sum for each of them. What's the theta bound on that? Like, I'll tell you there is a theta bound, like the lower and upper ones match. What is it? So think about if you were trying to write code to actually compute this thing, what that would look like.
Could you explain again what the theta bound means? I'm not sure I got it.
Sure. Okay, so up here, so omega means I can put a lower bound on it's going to take at least this many steps. O means an upper bound, it's going to take at most this many steps. And theta is what you use when those two match, when it's going to take like definitely this order of magnitude.
Okay.
Yeah. So just how many steps will this always take? Where like I define a step as something like simple, like addition, multiplication, storing something in memory, getting something out of memory.
Is it just going to be n-1?
Where do you get n-1 from?
The summation, like each one is doing the thing.
Yeah, you do have the summation. It would actually be n because I'm starting this from 0. It gets a little confusing, but anyway. Also, whenever I have n-1, I can just call it n because we're order of magnitude.
Right, gotcha.
Yeah, okay. So yeah, you're right that this is n steps, but is that all the work we have? Remember, this only defines one of the indices.
Oh, so is it n squared then?
It is n squared, yeah. So I'm going to call it n times n, and for each one, and this is for all of them. So this is in theta of n squared. Okay. In general, we don't really like things that run in n squared. Sometimes it has to happen, but usually there's something like faster we can do. Because like if you imagine I Fourier transform something with 1,000 elements, that's going to take 1,000,000 steps. Fourier transform something with 1,000,000 elements, which could easily happen in science. It happens all the time. Then you take 1,000,000,000,000 steps. Like n squared is what selection sort was, and we agreed that didn't look very efficient. And like it's absolutely worth going and looking into like the more efficient ways to do sorting, and I'll show you that, like the built-in Julia sort function and how fast that runs in comparison. But for now, let's just work on improving the Fourier transform. Okay, a little bit of math. I'll just leave this up for a minute and briefly review what we're going to do. So in the 60s, I think, these two mathematicians, Cooley and Tukey, got together and they figured out the Fourier transforms actually got a lot of like symmetry to it. I'm multiplying this like complex exponential thing, and complex exponentials wrap around themselves. If I do like e to the 2 pi I, that'll be 1. If I do e to the 3 pi I, that's the same as doing e to the pi I. So there's a lot of symmetry to it, and they figure, can we use that symmetry to, and this is -1, the famous Euler's identity. They figure out there's a lot of symmetry to this. Can we use that symmetry to make the computation faster? Like figure out where we're redoing some work and reduce that. So this is what they came up with. They said, let's split this into even components and odd components. And I'm just going to rewrite k as 2m in here. I'm going to rewrite k as 2m plus 1 in this one. I'm going to change the indices around so that works. And then I'm going to pull out this factor over here so that both of these look like they're in Fourier transform. Okay. Now, before we said we were doing about n squared amount of work. How much are we doing now? We're doing 2 subproblems, and these both now look like they're in little Fourier transform. But how big are the subproblems?
Would it be n squared over 2?
How do you get n squared over 2?
So each of them is like n over 2, because you have half the odd numbers than all of the numbers. And now you, that'll be for each indice, and now you have to like multiply it for all of them, right?
Yep, you have the right idea there. So like I've split this into 2 subproblems that are size n over 2, and the total amount of work in that is n squared over 4 plus another n squared over 4 for n squared over 2. There we go. Quick math trick, I've cut my compute time in half. But asymptotically, this doesn't really help us because we said we're just going to get rid of constant factors. So what they did was they just repeated this. And so they got this sort of tree of like, I've got a size n problem. I split it into n over 2 and n over 2. I split that further into n over 4 times. And I keep splitting till I get down to like a root level of 1 unit of work done here. In practice, you'd probably like actually just do the naive computation when you get a problem size that's small enough, like 32. There's a great blog post that I'll send on General later that shows off like exactly how much speed up you get by doing this. But yeah, how we figure out how much work this is, it's kind of a lot to just derive if you've never seen it before, is you notice that at every level, I'm not like reducing the problem itself. I still have to do n units of work here, n units of work here, n units of work here, and so on down the line. But I don't have n levels. How many levels do I have? And hint, it might be easier to just assume that n's a power of 2.
Is it just like n?
Well, it's not n because it would be n if I were doing this, n to n minus 1 to n minus 2 to n minus 3 and so on like that. Like if I had like 1,024 to start with, then this pattern would be 1,024 levels. But if I go 1,024 to 512 to 256 to 128 and so on down, that's like way fewer steps to get to 1. How many steps is it in terms of like a common function?
Oh, I think Pablo answered it. Log base 2 of n.
Oh, you did in the chat, right? It is log base. Oh, yeah, other people answered it. So yeah, thank you. So it's log base 2 of n, or we'll just say log n because wait, is this log n, because like changing constant factors around, like there's a log change of base formula that makes this change just a constant factor. So we usually don't specify what base log it is. Okay, so that means theta n log n is what the fast Fourier transform runs in. And this is a massive difference. So before, if I had like an n of 1000, I would do n squared is 10 to the 6, a million units of work. 1, 0, 0, 0, 0, 0, 0. That's a lot of work. But n log n, I'm just going to call it like, I'm just going to say it's the base 10 log here because it doesn't really matter. But that is just 3000. I'm saying it's log base 10. So there, I've saved so much work right there. And of course, on real computation, you're going to have like even bigger data sets and you get even more of a speed up proportionally. So I believe n log n is about the best you can do. I think there's some extra like tricks they do on top of that just to save memory that make this actually faster. But asymptotically, this is the fastest it gets. Okay, so I should have precompiled plots because plots never loads in time. So let's see this in action. I'll send the post, as I said later, where they did this for the fast Fourier transform. But let's actually do this. So this is the function that I showed you earlier that runs selection sort. And we're going to see that it actually is n squared, like we said. I'm going to make a random array, and I'm going to make sure that I got this implementation right. This is how you do assertions. You can do something very similar in Python that you've probably seen in like homework checking. It's just like, if this is true, it's not going to do anything. But if I assert like 3 is 4, then it's going to throw an assertion error. So if no errors are passed, then you're good. So I've shown that this does the right thing, at least that it matches like what I expect from the base function. Now let's time it using this timed macro from Julia. And IPython does something very similar that we used in homework 3, which, by the way, is due tonight unless you've talked to us about an extension. Anyway, so we see here that selection sort of this array with 100,000 elements in it. And it looks like this, by the way. It's just a bunch of random numbers that I got. Yeah, so selection sort and all of that takes 6.1 seconds. So kind of painful for something that we think should be fairly fast. So this matches our intuition if I probably don't like this algorithm. Base.sort, the built-in thing to Julia, uses an algorithm called quicksort. It applies to the exact same idea we just saw of like divide and conquer to sorting. And so it's got a very similar like derivation for being, I don't think it's actually theta n log n. I think it might just be, I think it might just be omega n log n. And there's some cases where it's n squared. But let's just say omega. But in the average case, on average, theta n log n. Yeah. Let's see how that does. Basically instant, same thing on the same array, but it took 0.02 seconds. So that's just a quick illustration of the amazing power of asymptotics. Let's even like try and plot this and see if these are the curves you get. So over here, I've got something to just make a range of like n's to go over. Don't worry about what this does. It's basically just picking like uniform spacing and log space. So going from like 2,000 to 100,000, I've picked like 50 numbers. And I've got this loop over here that's going to go over each of these numbers. It's going to generate an array of that length. It's going to sort it using the base sorting algorithm, and it's going to sort it using my selection sort. And it's going to take a few minutes on, not a few minutes, but a few seconds for sure on the last ones. And you see it like struggles more and more, and it's really just the selection sort that's struggling to keep up here. Okay. This would be a good time for any questions while we're waiting for this thing to catch up.
Is there any other faster way to do it than dividing and conquer? Or...
I'm not sure. There's studying sorting algorithms is a massive field out there. Do you mean sorting or the Fourier transform?
I meant for the Fourier transform one.
Okay. I don't believe so, not algorithmically, but yeah, I'm sure people have come up with speed ups. A thing I quite like is the fastest algorithm out there for doing Fourier transforms is called FFTW, the fastest Fourier transform in the West. It's kind of fun. But yeah, there is like a lot more theory to this. This is just like the basic idea of how most improvements work, I believe. Not 100% sure about like how things work in the state of the art under the hood. But once again, I'll send that blog post later, or we'll see. Also, we are now experiencing what is called in Julia the time to first plot TTFP problem. So this is a consequence of jitting everything, including your plotting library, because you know, plots usually don't need to be jitted. But they are very like labor intensive, and so if you just in time compile them, then it's going to take a while to compile everything. And so you suffer like when you include plots like at the very start and when you actually plot things. There's ways to work around this, like sysimages. Come ask me in office hours what those are. But anyway, we're done with this plot. And you see here, so first of all, this is log scaling. It's 10 to the 3.5, 10 to the 4, etc. like that. Selection sort, really not having a good time of it. And you see that's about quadratic. That's about n squared. This is one of the cool features of just-in-time compiling, actually. You don't waste any time on just like interpreting instructions. Once this has been just-in-time compiled once, like I did up there with the test, the only thing is going to be just the pure execution time. So this is pretty close to actually like an n squared type curve. Whereas down here, I see this base sort, and it's just like almost completely flat. Let's just look at that. Yeah. Base sort is taking so little time that we're not even really in the asymptotic regime yet. We're sort of jumping up and down because there's still like fluctuations based on what's happening on my computer. Whereas with selection sort, it's just being dominated by this asymptotic effect. But yeah, this is base sort is basically instant, selection sort is sluggish and suffering. Okay. So that's the power of like doing something that does the same problem in fewer steps. So there's two examples that I really like for asymptotics as it comes to physics. One's the Fourier transform, which I just showed you. The other is n-body integration. This is going to be a topic on the homework that is going to be released probably tomorrow or the day after, homework 4. And essentially that's asking like, if you've got a bunch of things interacting gravitationally, then how many units of computation do you have to do? You have to do like the 3-body problem is like one of the like simplest incarnations of this, of like the things that are easiest to just solve numerically. And in that case, you have to consider like the gravitational interaction between bodies 1 and 3, between 1 and 2, and 2 and 3. So you've got 3 units of things, and then that scales up when I've got like 1,000. You have to consider everything between 1 and all 1,000 of the rest, 2, well, all 999 of the rest, 2 and all 999 of the rest, and so on like that. What do we think that would be asymptotically? Very similar idea to what we've seen with selection sort and with the Fourier transform naively. And I'll talk about what's up on the screen in a minute.
Wouldn't it have an order of magnitude of n squared?
It would be n squared, yeah. So what you're going to be exploring on the homework is other algorithmic ways to speed that up, and not necessarily some others that aren't necessarily algorithmic, but are making use of like efficiencies in the problem to make it faster over time with the integrator. Okay, and you'll see what that means on the actual homework. But yeah, there's ways to speed that up massively because n-body integration is really applicable to like things like galaxy simulation, for example. Okay, right. In the last 10 minutes here, I want to talk about a slightly different issue which you'll also come up against, and which will come up again in our first lecture after the break on probabilistic programming and machine learning, which is numerical stability, and a few tips for dealing with it. Okay, so one of the most immediate ways you can see that this is an issue is by doing this. Like, often when we're like iterating over a bunch of numbers, we're told to do it like this in a for loop. For I equal to, I think it's 0, 0.1, 1, print ln I. You're told to do it like this, or if no one's told you, then I'm telling you now, you should do it like this. I'm going to say 1.1 just for consistency. Yeah, you should do it like this because this gives you the exact numbers. Whereas here, I'm adding 0.1 in each one. And then there's something weird happening. I go 0.1, 0.2, 0.3, a bunch of zeros, and then a 4. So this is attributed to something called like floating point error. And so this might not seem to be a big deal because you get back to like 0.4 later and 0.5. And even if it's not exact, it seems to not really matter. But then you start putting it through computations and you start doing things with it, and it does start to matter a great deal. So one really easy way this can come up is if I say like, if I equal to 1, print reached an integer, something like this. If I do this with a for loop, then that's going to be just fine. It's going to say I reached an integer. I should print out on this. Yeah. But if I do it in here, I'm never going to reach it because it didn't reach 1. It reached 0. All the 9s. So those kinds of like obvious checks are possible, but it's also possible, and we'll see in a few minutes with matrices, for these things to magnify and actually like eclipse your actual problem. Okay, another one is the limits of the data types we're using. So if we run 10 to the 18, I get 10 with, I guess that's 18 zeros after it. Like that looks about right. If we run 10 to the 19, I get this thing. That's not 10 to the 19. That's not 10 to the 18 with one more 0 after it. What happened here?
Is this machine error, like precision error, or is it something else?
Well, not exactly precision error. It's some kind of numerical error, something weird's going on, but why? This one's precision error. Like, what do we think could happen when we go to like really, really large numbers? And the hint is like, this is a different number down here when I put a float on it. Think about what the 64 means.
Pingshu says it's overflow, which I mean,
Yep, this
is
is overflow, yeah. Yeah, so if I do type of 10 to the 18, I'm gonna get, oh yeah. Okay, Pablo's asking where did the minus come from? Yeah, great question. So here's where it comes from. The 64 here means they have 64 bits to store this number. So if I give you a number that's too big to fit in 64 bits, and there's a whole, like, you can look up exactly how they use the 64 bits to store numbers. But 10 to the 19 is a number that's too big for that limit in integers. And so what happens is it wraps around from the biggest number it can possibly store. I'm not sure at the top of my head what that is. Is it 2 to the 64? Probably, yeah. 2 to the 64 is 0, but 2 to the 64, 2 to the 63 should be fine. Or, yeah, I'm not sure exactly where the limit is, but somewhere around here, it goes from the biggest number it could possibly be to the 53, maybe. No, that one's okay. It goes from the biggest number it could possibly be to something that is really small instead. It does have to do with 2's complement. Alad would be the perfect person to talk to about this. Yeah, this isn't sorting so much as just brute force. Yeah, it happens between 62 and 63. So I used a very bad naive method there, and I should have just written a loop. Yeah. So yeah, between 2 to the 62 and 2 to the 63, they hit the maximum number that they can store there. I'm not going to go through and find that manually. There's like a way. And so it wraps back around to the negative of that number. And so what you get is this thing. This is what you get after you hit the limit, you've gone back down to the smallest number you can store, and you add on whatever's left. Okay, and this happens in floating point numbers as well, but much further out. So it's 10 to the 308, that's fine. But if I go 10 to the 309, it just says that's infinity. That's like too big to comprehend. So there's all kinds of issues that can happen with floating point. So I maybe should have shown this a bit further up. You can ask Julia, you can also ask Python for the machine epsilon of a float, which is what's the smallest number you can store that like there's any kind of sense to. And it's this. So if I do 1 plus this, then it has like that little difference. It's like going to be indistinguishable, like half of this difference is going to be indistinguishable to the compiler. So you can ask for help on the epsilon. And here's a description of what machine epsilon is and why we care. Okay, so yeah, x plus epsilon x over 2 is infinity, even though this was a number before. So this is, yeah, here, they found the limit for me. If I do this plus a tiny bit extra, I'm not going to get a useful number. Okay, so in the last few minutes, what can we do about this? There's a variety of strategies, mostly just like be aware that it can happen. But one that comes up for me personally a lot is using types like rational. Multiple dispatch is a great thing for many reasons, including this one. Let's say I have this matrix system that like something like this literally came up on a homework I was doing like last week. And they were like, okay, here it's down to like a 2x2 matrix that you have to solve. It's not exactly this one. I picked this one just for like niceness. And so normally if you had like Python or MATLAB at your disposal, you'd like plug it all in and you'd get like numbers with a bunch of decimals that you would have to like write out on paper. I'd have to write out minus 16.087 or something like that. I have to pick how many significant figures I have. And I just really want to give an exact answer. And it's just kind of ugly. But with Julia, matrix multiplication, matrix solving works on numbers. A rational is a number. A rational is what you get when you divide like these two things. So if I do like 3 divided by 3 double divided by 2, then I get this thing, and I could pipe it to a float, and I get 1.5. But if I solve it as rationals, I don't have any kind of precision error, and I can just exactly write down what these are in fractions. Okay, so that's the one. A common workaround we're going to see in probabilistic programming is use only a number that fractions coding is like really underrated. Yeah. In probabilistic programming, we'll often work with a quantity called the likelihood of some data. And that can be like a really small number that's like really sensitive to these kinds of like little shifts. This comes up a lot, like just because real life data is messy. And so we need some way to make sense of it. In those cases, you should work with the log of the likelihood and not the likelihood, because really we'll be jumping around, we'll see next time, based on like, if this thing is more likely to do this, if this thing is less likely to do that. And those kinds of jumps, if you make them on the log instead of the number itself, then I get rid of these precision errors. I don't care what's in the 16th decimal place, because that's going to show up as like minus 16 or 0.34 versus minus 16.85 or something like that. So it's like it brings it back into the regime of numbers we can actually work with. The third is error amplification. Sometimes functions are going to, and I'll sort of speed through this. Sometimes functions are going to have really strange conditioning, meaning, I just need to do using linear algebra, whatever. Yeah, sometimes functions are going to do really weird things to your scaling. So for example, here is one here's a matrix that's ill-conditioned, meaning I might get drastically different like scales of answers depending on what I put in. And I see this in its like really big condition number, which is defined as its biggest eigenvalue over its smallest eigenvalue. There's a whole lot of like theory to this, but you see over here, if I multiply this thing, this relatively small input gives me a massive output. I put in 0.1 and things that are smaller than that, and I get like 39.5. And there is like, here's like the real world impact of that. Perturb your input by a little bit, you get a really big shift on your output. And there's some like eigenvalue, eigenvector stuff to figure out exactly what that is, but not super important to us. Just know sometimes functions can be really weird about how they scale different inputs. And you call this ill-conditioned, watch out for them. Okay, that's all we have for today. Sorry, I went just a little bit over. And remember to do homework 3 by tonight if you haven't asked us about an extension. And if you do want an extension, don't worry about it, just message me straight after.